So today we're going to be looking at arithmetic pattern recognition. This is the first jump into that we've had where we're starting to apply values to our concepts. And the other thing is arithmetic patterns involve a change that is constant via addition or subtraction. And one of the biggest things that we want to highlight is that it is a constant change. A constant change means that this pattern is not changing in the middle of itself. Oftentimes, students, people, professors want to kind of squeeze a pattern into something that it might not be. So let's take a look at a few of these things. Here we have a pattern, and we're going to start with our abstract before we make the translation into purely numerical. So with this, I have a square. Then I have these three little squares in this shape. And then I have 5 little squares in a continuation of that shape. So we can pretty much guess that, okay, my next one, I'm probably going to have my original 3 up here and my original 3 on the left, and I'm going to add in an extra square. Actually, let's do this in green. So there's my new square, and I'm continuing the pattern. If I continue us on in the next part, I'll have my original 4. 1, 2, 3, 4, 2, 3, 4, and we'll add another square. And then if I continue on one more time, I'll have this time 1, 2, 3, 4, 5, 2, 3, 4, 5, and we'll add another square onto the bottom and onto the right. Perfect. Now, this is the pattern. We don't have an issue with that. What we want to take a minute to notice is the constant change. So let's do this value in blue. We're going to say, how many squares do we have here? Well, we had 1. Then we had 3, 5. Here we had 1, 2, 3, 4, 5, 6, 7, 9, and 11. And what we notice is that the numbers are changing via a constant rate. From 1 to 3, what we did was we added 2. From 3 to 5, we added 2. From 5 to 7, we added 2. We added 2. And we added 2. So if we ask ourselves, what is the change? Well, that is a constant addition, which means by definition, this is an arithmetic pattern, and we can do things with arithmetic patterns. So the idea is if I want to jump to the, let's say, 51st term, I can manipulate these numbers without having to draw every single thing in the middle. And I can go straight to number 51 and tell you exactly how many squares it has and then draw it without drawing all the things in the middle. Let's take a look at number 3. So number 3, actually, why not? Let's go ahead and do 2 and 3. So if we look at number 2, what we're dealing with is that we have something like this where we have an ace of clubs, a 3 of clubs, and a 5 of clubs. I know these are cards, and I know that if I continue in this order of cards, I know the next one that we're going to have is going to be the 7 of clubs. We're going to have the 9 of clubs. But then we run into a problem because I don't have an 11 of clubs. I do have a jack, though. Perfect. So I've got the 7, the 9, and the jack. That kind of looks like a 3, so I'm going to... There we go. The jack. And again, this isn't too big of a deal. We can count the cards and move fairly accordingly. But if I translated these down into values, we know that the 3 and the 5 and the 7 and the 9 are no big deal. The ace and the jack, though, I have to give them numerical values. So the jack is the 11th number in the sequence, and the ace is typically the 1st. So that gives us, again, the ability to look at what's going on between them. We're adding 2. We're adding 2, adding 2, adding 2, and adding 2. We can make a pattern as to what comes next based off this constant addition. And then if we look at the next one, number 3, this one might be a little more difficult. But what we're looking at right here, and let's do this first set in purple, is I have part of a circle, a full circle, almost 2, and then 2.5. So the issue that we're going to run into is that I can look at this as whole units. And if I went with a whole unit, I would say, okay, I have a quarter of a unit, 1, 1 3/4, and then 2 1/2. But that doesn't necessarily lend me to see what's going on. Some of you might notice that, hey, well, we're just adding 3/4 of a unit, but we're going to take a pause and kind of roll back. If I have a quarter of a unit, it might be the easiest way to look at this instead by splitting it into, let's say, call these pizzas. Let's split these pizzas into slices. And if I have a fourth of a unit, I'm going to split them all into fourths. Okay, I'll do these as well. Okay, and now instead I'm going to look at the number of slices that I have, because that might help me out a little bit more. Well, the number of slices that I have right here is going to be one slice. I had 4. 1, 2, 3, 4, 5, 6. I had 7 slices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I had 10 slices. Okay. So, from here what we can do is from 1 to 4, I know that I am adding 3. From 4 to 7, I'm adding 3 again. And from 7 to 10, I'm adding 3. So I know how many slices are going to be in my next, let's call it pizza. Well, if I add 3, that's going to be 13. If I add 3, 16, and 19, which means that we can very easily draw 13 slices. I have 4, 8, 12, and then out of the next one, if I were to try and draw the full thing, that would give me too many, so I'm just going to say, okay, these don't exist. And I'm left with the 13th slice. For 16, 1, 2, 3, 4 full pizzas. For 19, 4, 8, 12, 16. That'd give me 20. I can't do that, so I've got to cut out one of those slices right there. There we go. Now we have 19 slices. And what you'd see is the fact that we're adding 3 each time. Perfect. And furthermore, what you could do is you could say, well, okay, if I'm not actually a value of 13 right here, you could say, well, this is 13/4, this is 16/4, and this is 19/4 if you want to count them as whole values. But realistically, we've manipulated the numbers so that we can get the next sequence in the pattern. Perfect. So having said that, what I want you to try is I want you to try a few of these. Go ahead and try number 4, 6, and 8 on your own. Pause the video, unpause it when you're done, and see how well you did. Okay. So, assuming you've had a shot to look at it, let's look at this. So from 1 to 5, what we did was we added 4, we added 4, and we added 4. So we can safely say that the pattern here is going to be adding 4. So if I keep that pattern going, add 4 to 13, I'll get 17, 21, and 25. Easy enough. If we look at number 6, from 2 to 4, we added 2, we added 4, and we added 8. Okay. So with this one, we can predict what the next terms are. However, we're going to say that it is not a constant add or subtract. It's not constant addition or subtraction. So therefore, the only plausible answer is that this is just not an arithmetic pattern. We could predict it, but we're not going to look at this type of pattern until a later topic. So that's just not arithmetic, and we're going to stop right there. Number 8, let's see. In this one, we're not adding, we're actually going down. We subtracted 9, and we subtracted 9, which means my constant rate of change is taking away 9, which is going to leave me with a negative 16, a negative 25, and a negative 34. Awesome. Okay, and so the next couple, we're going to have to look at these a little differently. With this one, I have 1, 6, and 11. Now, this one is written out, so the best way that I might be able to do it is by writing out what these values are. So if I have 1, 6, and 11, that makes my life very easy, because then I can look and say, hey, that's add 5, add 5. That's a constant rate of change. I can just add 5 and get my answer of, let's see, add 5, I'll get 16, then I'll get 21, and then I'll get 26. And you might be tempted to say, boom, there's my answer, but let's go back and remember with the abstract patterns, I can't just spit out a number and say that that's my answer. I have to translate it back into the original scope of the problem. I was dealing with circles, so I put my answer in circles. With this one, I can't just write out my answer as a number. My original question was in written out numbers, so this shouldn't be too bad. It's 16, 21, and 26. And this is my final answer. Not what's written in blue, what's written in black. Perfect. Same thing going on with this one. We're going to take a look at this one and see how it does. We have negative 12, negative 26, and negative 40. Okay, so if that is a negative 12, negative 46, and negative 40, okay, this looks like this is getting more and more negative, so I'm going between and between. I know I'm taking away because my negative is getting larger in value. Let's see, 2 to 6 is going to be 4. Oh, 26. That's why. I was like, wow, that's not consistent. But okay, so that's going to be minus 14. And then here it's a minus 14 again. That's going to be constant. So again, we may be tempted to write out our answers as, if I subtract 14, we'll get, let's see, negative 54, negative 68, and then negative 70, 82. But again, we're going to put our final answer in, not in the numbers, but in the written out aspect of that. Let's see how tiny we can write. And there we go. So we have our answer right there in black. So now that we've seen a couple ways of how to work the numbers, you don't necessarily need to work them in the orientation that they were, but you can manipulate them, especially with these. Why don't you try number 14, pause the video, unpause it when you're done, and see how well you did. Okay, so now that you've had a chance for it, I notice I go from a fraction to a whole number to a fraction, and I'm like, okay, what's the difference between 11/4 and 4? I don't know about you, but I can't necessarily just snap my fingers and do that in my head. So what I'm going to do is I'm going to translate these into all fractions. Because I have fractions right here, I want to turn this 4 into something that's a fourth, which means kind of like my circles up here, I'm going to split the whole number into fourths. So, okay, if I have 4 pizzas and I cut them each into 4 slices, that'll give me 16 fourths. And that makes my life a lot easier because what I can focus on at this point is I can focus on just the top numbers. From 11 to 16, we added 5. And from 16 to 21, we're adding 5. I can't fit that in there, so I'm just going to write it over here. So we add 5, we add 5. So our next number should be, let's add 5, 26. Next number up top is going to be 31, 36, and they're all over 4. And again, we'd be tempted to write that as our final answer, but our original problem was in reduced format, so we're going to go ahead and we're going to reduce these. So my 26 over 4 reduces down to a 13 over 2. This one doesn't reduce, and this one reduces down to the whole value of 9. Now, if this was in an unsimplified form, I could leave my answer right here. If this was in mixed numbers, I'd make my answer in mixed numbers. But my answer is in fully reduced improper fractions, therefore I'm going to stick with fully reduced improper fractions. Perfect. And so let's take a look at the last one, number 16. Would you describe arithmetic series as being convergent or divergent, and why? So by the definition of what we talked about last time, we discussed that divergent tended towards infinity. Namely, divergent has to go towards both infinities, so negative infinity and positive infinity. Convergent is something that converges on a specific number. Like we went with 0. Realistically, that number can be any number, and divergent has to be both. So an arithmetic series, we know either approaches if we're adding some value, it either approaches infinity or negative infinity. And because it approaches or, it's not going towards both. By definition, an arithmetic series is neither convergent nor divergent. It doesn't approach one value, although a statement, a case could be made that say it approaches infinity, it converges on infinity, but infinity is not necessarily a number. So because it's not a finite number that it's approaching, like 0 or 1 or 10, and it's not going towards both infinities at the same time, it is neither. And we'll just make that case right there. And that's a decent explanation why. The challenge question, what you might want to try on your own, is try and draw your own arithmetic sequence and have a classmate predict the next 3 parts. So pull out mom, dad, brother, sister, draw an arithmetic sequence and see if they can't figure out what's going on next. But it's going to lead us into the next piece. And the next piece is where we're taking those arithmetic sequences and applying them into what we have right here, a Cartesian plane. And we're going to see our first linear graph. Now, our Cartesian plane typically has 2 values. It has both an x and a y. What we're going to do is we're going to call each one of these a specific number, or let's going to call this 1, 2, 3, 4. So the first term, second term, third term, fourth term, first term, second term, third term, fourth term. Okay. So let's see where this is going. So with my x and my y, I have 5, 15, 25, 35. It looks like what I'm doing each time, I added 10, and added 10. Okay, so this graph seems to be increasing. And so let's go ahead and let's graph it and see if it's converging on a point, diverging away from a point, or if it's neither. And let's do the graph in blue. Okay. So if my first term, 1, 2, 3, 4, yep, so we have space. So if my first term is going to be 5, I need a span to go up 1, 2, 3, 4, 5 units up to fit 35. So I'm going to make my scale, if I call this 35, I'm going to have to do my scale by 7s. So my last number is up here. That's going to be 28, 21, 14, 7, and 0. And a quick and easy way to tell what your scale is going to be is take your largest number, 35, and divide by the number of blocks, 1, 2, 3, 4, 5. So 35 divided by 5 is going to be 7. So each block is going to be a difference of 7. Okay, let's plot our points. Yeah, let's keep doing this in blue. Okay, so I have nothing on 0. My first unit is 5, 15, 25, somewhere in this neighborhood. And the fourth unit is going to be 35, which is that top number. And so what we notice that this pattern is doing as we head off to the right is that it's going up. It's not bending, which means it's not convergent. It's not oscillating, so it's not divergent. It is going to be neither. Okay. And lastly, we're going to ask ourselves, can we write the equation? Okay. Well, if I wrote the equation, all we need to do is trace this back one more so I can hit that y-intercept. Okay, so if I'm going back and I subtract 10, if I subtract 10 back here, that's going to be from 5 is negative 5. Okay. So if I have y equals mx plus b, I know my intercept right here is -5. And I know my slope is going to be 10. 10x minus 5. There's my equation. Okay. If we jump off into the next one, ooh, it looks like this one is going down. So our first term right there is 51, 35, 19, 3. Okay. So from 51 to 35, it looks like we went down 16. Here it looks like we went down 16 again, down 16. So we know that our rate of change, as we discussed previously, is going to be -16. It's going to be a -16x. Don't know what that term is. I'll have to graph that and kind of see what's going on. But, okay. Let's figure out what our scale needs to be. My largest number is 51. I have 1, 2, 3, 4, 5 blocks. So 51 divided by 5 is going to be, let's see, 10.2. So I'm going to make each block worth 11. So I'll have 11, 22, 33, 44, 55. Perfect. So the first unit's at 51, 35, 19, and then 1, 2, 3. The fourth term is going to be 3, and that's going to be way down here. Okay, so I don't see it bending towards something, so it's not convergent. I don't see it oscillating, it's not divergent, it's going to be neither. This one, because it's a -16, it's going to be decreasing. Perfect. Oh, and we need to figure out what our intercept would be. Well, it looks like if I'm going this way, I'm adding 16. So let's go back one more to add 16 to this. So 51 plus 16 is going to give us a 67 equals that. There we go. Perfect. And last one, why don't you go ahead and pause the video, unpause it when you're done, and see how well you did. Okay, now that you've had a shot to try it out, let's go ahead and take a look. So with this one, I'm going, looks like down. So I know this is going to be a decreasing trend. 573 to 521, that's going to be a decrease of, let's see, 52. If I take away 52 again, yep. If I take away 52, that's going to be 67, yep. Minus 52. Yep. I just wanted to make sure it was consistent there. So if I'm subtracting 52 each time, I know that my slope right here is going to be minus 52. Negative 52x. I don't know what the y-intercept is. I'm going to have to figure that out here in just a moment. Nextly, I need to figure out, okay, I need to draw this, and I need to figure out a scale. So I have 5 blocks. I have 573, and I've got 5 blocks. So I'm going to divide that by 5. That's going to be 1, 1, and then 23, 4 point something. We're not going to worry about that, but it's going to be 114, so I'm going to round that up to 115. That's going to be how much each block is worth. 115, 230, 345, 460, 575. Perfect. So my first unit is 573, almost right at the top. Then it's going to be 521. Call that right there. My next block over is going to be 469, so I'm just above my 460 mark, and then 417, we're just below it. So if I drew this right, it's doing that. So we know it's decreasing. Yeah, so we have a decreasing pattern. It's not converging, so we don't see a bend towards some value. I don't see it wiggling. It's neither. The last thing we need to do is if I'm taking away 52 each time and I want to move back to see where that hits the y-axis, I'm going to need to reverse the process. So I'm going to add 52 to 573. 5, that's going to give me a 12, 625. And there we go. Perfect.